Alright, Titans, hello and welcome to Chapter 7, Section 1. Chapter 7, Section 1. Here in Chapter 7, Section 1, we're going to be solving systems of equations by the graphing method. There are three different methods that we will discuss here in Chapter 7. One method of solving systems of equations is to solve them by graphing. That's our first method. To use this method, what you do is you go ahead and you graph both equations on the same coordinate plane. The point where they intersect will be the solution for the system. Here in Chapter 7, Section 1, solving a system of equations by the graphing method, we want to first of all go ahead and talk about the steps that are needed to complete this method. To solve a system of equations by using the graphing method, it is really quite simple. The first step is to graph your first equation. The second step is to graph the second equation on the same coordinate plane. The third step is simply identifying the point where the two lines intersect. The point where the two lines intersect is the solution to the system. Now let me go back to step 1 and step 2. It is very important when you do step 1 and step 2 that both of your equations be in the form of y equals mx plus b. Those two equations must be in slope-intercept form in order for us to successfully graph both equations. Once you've completed the three steps, you've solved the system by the graphing method. Let's go ahead and take a look at an example of solving a system by the graphing method. Here in example number 1, we're given two equations, y minus x equals 1 and y plus x equals 3. Now if we take a look at these two equations, they are not in the form of y equals mx plus b. Yes, the y is first, but the x term is on the left side of the equal sign. We want the x term to be on the right side of the equal sign. So what we're going to go ahead and do first to solve example number 1 is put these two equations into slope-intercept form. So we'll first of all go ahead and take a look at the blue equation. To get the blue equation into slope-intercept form, we need to take that minus x and move it over to the right side. When minus x changes sides, it changes signs. It becomes a positive x. Now the blue equation is in slope-intercept form. If we go ahead and take a look at the red equation, in the red equation, to get y by itself, we need to get rid of plus x, so we're either going to subtract x from each side, or once again use the strategy of change sides, change signs. So if we move plus x over to the right side of the equation, it becomes negative x. Now, both equations are in slope-intercept form. That's going to allow me to graph these. So I'll go ahead and graph the blue one first. I mark the y-intercept at a positive 1, and then I mark off a slope of positive 1, which is up 1 over 1, up 1 over 1, up 1 over 1, and then I can draw my line. Please make sure that when you do this by the graphing method, you extend your lines. You're not going to be sure where the graphs are going to intersect. So it's important to extend those lines all the way across the coordinate plane. So notice here, I'm getting that line so it extends all the way across the coordinate plane in an accurate manner. I will then go ahead and graph the red equation. I'll mark my y-intercept of a positive 3, my slope of negative 1, so down 1, right 1, down 1, right 1, and I'm going to extend it all the way across the coordinate plane. Then when I accurately draw my line, I will be able to see where these two graphs intersect. And that's the point, positive 1, positive 2, 1, 2. X value of 1, y value of 2. That's the ordered pair that when I plug it in to both equations, it will test to be a solution. And it's always a good idea to go ahead and do that. You can check your work. That way you know if your answer is right or wrong. Alright, we'll go ahead and move into the second example we have here of solving by the graphing method. If you look at this example, the setup of the two equations that's given to us is in slope-intercept form. So since these two equations are given to us in slope-intercept form, we can go ahead and graph them. So we plot the y-intercept, we mark off the slope. And once again, make sure you mark it all the way across the coordinate plane. We take the second equation, we plot the y-intercept, we mark off the slope, and once again, mark it all the way across the coordinate plane. Now, if you notice, these two lines are parallel. Parallel lines do not intersect. So if the answer is where the two lines intersect, and the lines do not intersect, then there's no solution. So this would be what we consider one of those special cases. If your two lines do not intersect, then there is no solution. That's something you want to be aware of when solving a system of equations by using the graphing method. Alright students, we'll go ahead and take a look at the last example here. To take a look here at the last example, we notice that both equations are not in slope-intercept form. So since these equations are not in slope-intercept form, we need to go ahead and first of all put them into slope-intercept. So what we're going to do is we're going to go ahead and take the negative 2x and move it over. We're going to take the 8x and move it over. Remember, the goal is to isolate the variable y. When negative 2x changes sides, it changes signs. When 8x changes sides, it changes signs, as you can notice down below. Now, on the second step, we need to go ahead and get y by itself. So to get y by itself in the blue equation, we need to divide everything by 3. That will go ahead and give us our equation in slope-intercept form. In the red equation, we got to go ahead and divide everything by negative 12. When we divide everything by negative 12 and simplify, that will give us the equation that we've drawn the arrow to down below. Now, it did not look like this at first, but now if we look at the two equations, we'll notice they're the same equation. Well, if they're the same equation, they're going to lie on top of each other, and they are going to intersect at every single point. So if they intersect at every single point, there's an infinite number of solutions because the lines are what we call coinciding. They're on top of each other. So students, this is your second special case. Anytime you have two equations and they turn out to be the same equation, then they're going to lie on top of each other and they're going to have an infinite number of solutions. So that would be your answer. Infinite number of solutions. Alright, solving a system by the graphing method. This wraps our lesson. It's now recommended that you try problems 4, 5, and 6 on page 323 in the guided practice section of your textbook. By doing these 3 problems, you're just reinforcing the concepts that we went ahead and covered in our lesson here today. The answers to these questions are listed below here. The only one I need to make a change to is number 6. Number 6, it is not negative 2. Negative 3. Number 6 is one that does not intersect at an exact coordinate. Number 6 is what we call an approximate solution, and you're going to find that number 6, if you graph it correctly, should intersect at negative 1 4/5. That would be the exact intersection point for the x value, and the y value would be negative 2 4/5. So it's very close, as you can see, to negative 2, negative 3, but not exact. And it is a possibility that when you solve these by graphing, they will not intersect at an exact coordinate. And we don't say, well, okay, this is the closest coordinate. We're trying to be precise. So sometimes when you do these problems, you may end up with an answer where the x value and the y value are not integers. That concludes our lessons. Once again, if you have any questions, please see Mr. Spilker or Mr. Simpson. We hope this tutorial over Chapter 7, Section 1 can help you understand the information and be ready to come in to class tomorrow to practice Chapter 7, Section 1.
Made with Doodlecast Pro.